Have you ever wondered if the universe hides a secret pattern, a design more intricate than anything humans have ever uncovered? Well, get ready, because today we're diving into the world of Penrose Tiling and Quasicrystals, a beautiful, rule-defying playground of symmetries that shouldn't even be possible, yet somehow exist. Sound boring yet? Tough luck. This one's going to twist your understanding of reality. So, grab some coffee or tea, or whatever fuels your head for mind-bending dives into the cosmos. Shall we? Let's begin. Okay, quick scene setting. Back in the day, crystallography, the study of crystals, was a bit like a grid-obsessed math teacher. Crystals were thought to be these neat repeating patterns, like wallpaper that went on infinitely. You know, order, symmetry, predictable beauty. Everything was falling into place on a predictable grid. Enter Roger Penrose, the guy who practically opened a whole new dimension in geometry during the 1970s. And mind you, this was before he got into black holes and Nobel Prizes. He introduced something revolutionary: Penrose tiles. Imagine two types of tile shapes, a fat kite-like one and a thin dart-like one. These two shapes create a pattern that never, and I mean never, repeats exactly no matter how far you extend it. And wait, here's the kicker. It's still perfectly ordered. Now hold on, isn't that a contradiction? Something can't be ordered and non-repeating, can it? And hey, I can feel you skeptics out there saying, sure, but this is just some mathematician noodling around on graph paper. How could this have any connection to, let's say, physical reality? Oh, but here's the plot twist. Fast forward to 1982. Scientists, while analyzing an aluminum-manganese alloy in a lab, found a crystal, but it wasn't like any crystal anyone had ever seen. It matched a Penrose tiling pattern. What? Brace yourself for a shock, because this meant that nature, real deal nature, created a structure that doesn't fit the ordinary rules of crystallography. And the science world? Let's just say it freaked out. They called it a quasi-crystal. So here's the gist. Quasicrystals introduced a middle ground between order and randomness. It's like a symphony where notes don't repeat, yet there's an innate harmony. In physics and chemistry terms, their atomic arrangement neither repeats nor dissolves into chaos. And why should you care? Because this little mind bender pokes at some pretty fundamental questions about how matter organizes itself. All right, let's go hardcore for a second. In crystallography, symmetries are kind of like a no-fun parent. Other crystalline structures were constrained by the shapes that repeated over and over. Then, quasicrystals appeared with forbidden symmetries, shapes like pentagons with five-fold rotational symmetry, something your standard crystals could never accommodate. If you spin a crystal and repeat its atomic arrangement, it only likes two-fold, three-fold, four-fold, or six-fold rotations. Because good old mathematics says higher fold rotational symmetry, like the eerie five-fold symmetry of Penrose tiling, is impossible for normal periodic crystals. Impossible, except for these rebels, the quasicrystals. Remember, not random, but non-repeating. Picture it this way. Imagine you're tiling your floor and the tiles cooperate like a choreographed dance, but they refuse to create an exact pattern. Every step gets more surprising, yet the tiles still seem to talk to each other in code. Organized, brilliant chaos. Now, let's pivot and hit on the scientific implications. The discovery of quasicrystals opened the floodgates to debates about the very nature of matter and the universe. First, materials science. The unique arrangements give quasicrystals incredible properties. For instance, they don't deform easily under stress, making them perfect candidates for non-stick frying pans. Goats have no clue how much science is helping their human friends out here. Then, there's the deeper puzzle. Do quasicrystals naturally exist beyond Earth? Short answer, yes. They've even been found in meteorites. That's right, these impossible, rule-breaking structures heralded from space itself. What does that mean for the physics of star formation or material evolution? Nobody really knows, yet. Also, Don't even get me started on how these patterns relate to wave functions in quantum mechanics, or even some cutting-edge approaches to string theory. Oh, and did you know Dan Shechtman, the guy who discovered quasicrystals in 1982, was initially laughed out of the room by his peers? They thought he was nuts. It wasn't until years later that he won the Nobel Prize for proving the world wrong. How's that for perseverance? Now, before we land this hyper-focused plane, let's whirlwind through something many wonder. Could Penrose Tiling influence human-designed spaces on a massive scale, like architecture? After all, if nature's secretly favoring quasi-crystal-like order, we've got some catching up to do in the design world. Would living in a never-repeating, quasi-crystalline-inspired space change how you feel about home? Mess with your psychology a bit? Fascinating possibilities, no? In summary, this episode wasn't just about tiles and crystals. It's a saga of curiosity, rewriting the rules of what counts as possible. So, tell me, has this shifted the way you see the world? Did Roger Penrose's quirky tiles or Shechtman's rebellion against science conventions blow your mind a little too? Make sure to comment, like, and subscribe. I'll be back soon to roll out more of the universe's most jaw-dropping enigmas. Stay hyper-focused, and never, ever doubt the unexplored magic hiding behind simple shapes and symmetries in our world. Because guess what? Symmetry doesn't play by the rules, it makes them.